The vast universe is an endless source of inspiration, not just for art, but also for science. Since humans first set foot on the moon, we've been wondering, where is the greatest limit we can reach? Is science fiction too far from reality? Are we the superior species in the universe? And are we alone in this vast cosmos? Those are many questions, so to start this journey, let's answer the simplest one. Are we the superior species? We are curious beings. Once we realized that there's a whole huge world above the sky waiting to be explored, we've tried every possible way to conquer it, from airplanes to rockets, and finally, Neil Armstrong's footprints on the moon. One small step for man. After discovering there's so much more to learn out there, we began to realize our place in the universe, a tiny species on a tiny planet, perfectly positioned between the ideal conditions for life. Not too close to the nearest star to burn us, not too far to freeze us. And somehow, time gave us a little satellite and a ring of asteroids surrounding us to protect from the dangers of space. We're incredibly lucky to have ended up in this fascinating zone. That luck makes us think about our existence. Are we the superior species in the universe? And if not, what would make us superior? To understand where a species stands in the universe, or more specifically, how developed they are, we need to look at the research of Soviet astronomer Nikolai Kardashev. In 1964, he introduced a scale named after him to measure the development of hypothetical civilizations in space. Based on a simple yet convincing idea, the more advanced and modern a society or civilization is, the more energy it needs to supply its entire population, run various machines, and exploit that energy to the maximum. To understand this scale, we need to know why he chose energy consumption to determine development. We are living beings, and in biological terms, we're machines made of countless cells living by metabolism. Metabolism is what keeps our form intact, fixing our body into a unit. And to do that, we need energy. We take in energy in many ways, the simplest being eating and drinking. And to eat and drink, we have to move. In the early days, humans knew only how to hunt and gather to survive. Over time, humans became more advanced, and we shifted from hunting and gathering to farming, and then from farming to industry. Technological progress has allowed us to make breakthroughs in life and find ways to extract more energy, use it more efficiently, and even travel through space. Looking at the entire time humans have existed on Earth, the hunting and gathering period took up about 90% of that time. Just 20 years ago, we thought it was a fantasy to own a supercomputer with internet connectivity and the ability to make calls in our pockets. Energy is at the core of every civilization. Without energy, we can't survive, and the more energy we use, the faster we develop. So, we now have a basic understanding of this scale. What does it specifically look like? A Type 1 civilization is one that has fully harnessed the energy available on its home planet. Fully harnessing doesn't mean exhausting all the oil on Earth. On the contrary, it means we've learned to use everything Earth offers in the most efficient way. For example, wind, water, and natural phenomena like volcanoes and storms. To do this, humans need to find ways to minimize the use of fossil fuels and improve the current state of the planet. This might sound like a dream, but in reality, humans are capable of developing technology incredibly fast. In the 1960s, computers were as big as buildings and had only 1 megabyte of RAM. But today, we have supercomputers with 16 gigabytes of RAM in our hands. So, over time, technology will only develop faster and stronger, and the dream of optimizing the available energy on this planet will just be a matter of time. In short, level 1 is when humanity has figured out how to harness all the available energy on its planet without worrying about running out in the near future. But what if humans keep developing and need more energy, that's when we reach a Type 2 civilization, one that looks to the biggest and closest energy source available, the sun. The energy produced by the sun is immense, and we've only managed to use a tiny fraction of it through sunlight. To fully harness the sun's energy, or any star's energy in the universe, we'd need a machine called a Dyson sphere. A Dyson sphere deserves its own video, but for now, let's just say it's a massive structure built around the sun to optimize the collection of its energy. The mass of the sun is 1.989 times 10 to the 30th power kilograms, and its energy isn't just light and heat. So, if we consider the sun as a giant battery, we'd probably never need to recharge it. With almost infinite energy from the sun, we could make technological breakthroughs beyond imagination. At this level, we could completely migrate to other planets within our solar system that could support life, like Mars or Jupiter. For a Type 2 civilization, humanity would seem like primitive creatures that haven't evolved much yet. But even that is nothing compared to a Type 3 civilization. After settling and thriving in our tiny solar system, there's something even bigger, farther away, and more powerful waiting for us: the vast Milky Way galaxy. To reach a Type 3 civilization, we'd have to harness the energy from the entire galaxy. At that point, humanity would have entered the age of galactic civilization. Much like the space movies you've seen, we'd spread out across the galaxy, able to draw energy from any star or planet we choose. A single Dyson sphere wouldn't be enough to cover the whole galaxy, so we'd need something like a Dyson swarm. We might even build a Dyson sphere around a black hole in the center of the galaxy and create black hole bombs, concepts that are hard to explain in just one video. With the vast distances between stars, the speed of light just won't cut it. So, to travel between different districts of the galaxy, we'd need wormholes. All those science fiction concepts you see in movies, they would become easy to achieve once we reach Type 3. But what about Type 4, 5, or even 6? While we'd love to imagine the wonders humanity could create at that level, the truth is, the further we go, the harder it is to predict what could happen. They might have mastered the galaxy by then. They might have found ways to stop aging, or maybe they've created such advanced algorithms that AI beings within it think they're real humans, making YouTube videos about a far more advanced civilization that has built a matrix. Whatever the case, after Type 3, it all becomes too unimaginable. It's still a dreamland for now. So, where are we as humans on this scale? As we mentioned earlier, a Type 1 civilization on the Kardashev scale can harness the maximum energy of Earth, but the reality is, we still struggle with fully tapping into everything nature has to offer. So, what type are we? Type 0? In 1973, astronaut Carl Sagan estimated that humanity was at a 0.7 level, and by 2021, we were at 0.73. While the number isn't huge, it's clear that we've seen how much our lives have changed. We can believe that once we reach Type 1, things will improve dramatically. Physicist and futurist Michio Kaku predicts we'll hit Type 1 in 100 to 200 years, Type 2 in a few thousand years, and Type 3 in 100,000 to 1 million years. And if we're not the only life forms in the universe, it's likely others are on a similar path. We just fear what we don't understand or can't control. And in this vast universe, the most mysterious and uncontrollable thing might just be life itself. So, where are the aliens? Do they exist? And if they do, are they here for peace? To these questions with the Fermi paradox. Before answering, we need to understand what makes life possible. Looking at our little blue planet, we must admit we're incredibly lucky. Earth is perfectly placed in relation to its nearest star, the Sun. It's not too close to burn like Mercury, nor too far to freeze like Uranus. This perfect spot is called the habitable zone, where conditions are just right for life to thrive. In this zone, the temperature is neither too hot nor too cold, allowing water to exist in liquid form, cells to grow, and life to flourish. Every solar system has a planet like this, and Earth is the only one in our solar system within the habitable zone. For aliens to exist, they'd need to live in these perfect zones too. So, if we count the number of solar systems with habitable zones, we can figure out where life might be. NASA estimates that just in our Milky Way, there are at least 100 billion stars. And if we look beyond into other galaxies, there are over 100 billion more. That means if all galaxies are similar in size, the universe contains more than 10 quintillion stars. If only 0.01% of those stars can support life, there are already countless places where life could thrive. In fact, according to Inverse.com, in 2013, astronauts counted at least 6 billion Earth-like planets in our galaxy. With 6 billion potentially habitable planets, surely aliens must have shown up by now, right? Sadly, no. In contrast to the enormous potential mentioned above, the extraterrestrial life we have discovered since we began exploring the universe is absolutely non-existent. So why, with so many conditions in place, have we still not encountered any extraterrestrial beings? This is the Fermi paradox. The paradox is named after the physicist Enrico Fermi, who described the stark contradiction between the high likelihood of extraterrestrial life and the complete lack of evidence to confirm its existence. This is quite terrifying, because we don't know whether we are truly alone or if we simply haven't looked closely enough. To explain this paradox, Fermi proposed the hypothesis of the existence of extraterrestrial beings known as the Great Filter. Our universe has existed for nearly 14 billion years, and no one disputes its vastness. Yet, despite this enormous span of time, the universe seems eerily empty, with no signs of advanced civilizations. From here, scientists hypothesize that there may be something preventing humanity or other civilizations that may have once existed from advancing to the point where they can contact higher civilizations. This something is an event, a form of selection to determine whether a species is capable of developing further. If it passes, congratulations, you've been selected to join the ranks of advanced civilizations. If not, that civilization will be wiped out. This is the Great Filter, a decisive turning point in the development of a civilization, or even its survival, where everything is at stake. However, the theory of the Great Filter isn't limited to just this. Scientists have divided the Great Filter into two possible scenarios. One is that the filtering process has already occurred, and the other is that it still awaits us in the future. Each scenario leads us to different assumptions about the future of humanity. So, what exactly will happen to us? Will we face the consequences of the Great Filter? In this case, humans are the only intelligent species that survived the MEM filter of God. First, for extraterrestrial life to occur, it requires life itself. Life is an incredibly complex factor in Earth's history, and scientists are still uncertain about exactly what happened. We only know that, from unrelated molecules, cells began to form and became life. The first filter may come from the fact that life did not form, or it did not happen on planets within the habitable zone. What about places that do have life? During the development of life forms, something happened that caused other species to fail. It could have been a massive disease that wiped out all life, or it could have been a giant asteroid impact, like what happened to the dinosaurs. Whatever happened, we know that humanity survived, which makes us the pioneering species, the first in the universe capable of exploring the vast world out there. But this doesn't mean that the Great Filter is the only one. After this, there may be other filters still ahead of us. And from here, we enter the second scenario. The Great Filter has not yet occurred. This scenario is more widely believed, as it explains why we still haven't found any extraterrestrial civilizations. In this case, the Great Filter could be an event that only occurs with advanced civilizations. Somehow, these civilizations reached extinction before achieving Type 2 civilization status and could venture into space. The event could be an artificial intelligence uprising with plans to wipe out humanity, or perhaps they fired nuclear missiles at each other and self-destructed. Another more realistic scenario is the possibility of a highly contagious artificial virus that kills every organism it encounters in a short period of time. Regardless of which scenario occurs, this catastrophe would lead the species to an irreversible state, extinguishing intelligent life across the universe and preventing us from ever receiving a greeting from them. According to this scenario, extraterrestrial life does exist, and we are not alone in this vast universe. But before we get excited, we must first face the unfortunate truth. If the Great Filter applies to advanced civilizations, it means that we will also have to face it. And it is likely that we have not yet encountered extraterrestrial beings because they have already gone extinct. So, if one day in the future, NASA announces that they have discovered the remains of an extraterrestrial civilization, don't rejoice too quickly, as this could be evidence of the impending end of humanity. Sadly, the answer to this question is not a pleasant one. If extraterrestrial life doesn't exist, it means we have the mission to become the pioneering species, to be the first to explore this universe alone, before any other species is lucky enough to overcome the Great Filter of life. But if they do exist, it means the painful end awaits us on the horizon. No matter how much we struggle, no one can escape it. And from the most objective perspective, humanity has only existed for about 6 million years on Earth, less than 0.1% of the universe's age. Everything will continue while we, once dust that could sing and paint, will eventually vanish. And who knows, one day, far in the future, another creature somewhere may broadcast across this blue planet and wonder if they are alone in this universe. By now, everyone is surely familiar with Elon Musk and his idea of reaching Mars. This is an extremely risky project, often considered unrealistic in our current era. But why is it risky and unrealistic? Can humanity pull it off? These will be the questions we explore today. Before we talk about living on Mars, we need to understand the process and mechanics of colonization for one very simple reason. The act of going to Mars to live is, in fact, a process of colonization. Essentially, we will go to a new land, assess its suitability for settlement, and then prepare for a large migration to conquer it. But not stopping there, in order to settle, the migrating group must create the capacity for self-sufficiency so that they are not dependent on Earth. After some time, this migrating group needs to develop and cultivate the land, bringing back goods to Earth to establish trade, creating the conditions for future prosperity. To accomplish these tasks, a migration group needs to go through specific steps. The first thing we need to do is find a location to implement the colonization plan, just like Christopher Columbus when he found India in the Atlantic Ocean. After unintentionally discovering a new land, the first thing we need to do is determine its location on the map and prepare for landing. Once we land, we can start researching whether the place is suitable for improvement and supporting life in the long term, such as checking if there are sources of water, vegetation, and if the climate is suitable for living. No one would want to transform the Sahara Desert into a new home. It would require too much effort and resources. Therefore, finding a place that can be improved is crucial. Once we confirm that the new land can support life and be improved, we need to send the news back to the motherland to proceed to the next step. After understanding the island and having enough manpower, the next step is to figure out how to survive on the island. We will start primitively by building small huts, living together in a community, and beginning to clear the land. During this phase, because we can't yet provide for ourselves, we will rely on supplies from the mainland while simultaneously adapting to the environment and stabilizing our lives. However, we will still use what is available on the island to survive. We start farming. Although the yield is small, it is the first step in the colonization of the entire island. The initial farming phase may be difficult, but once we establish a stable farming system, we can gradually become self-sufficient on this new land. Once we have enough food to sustain ourselves, we will no longer depend on supplies and can begin the next phase. Becoming self-sufficient isn't too difficult. What we need is time. Once we achieve independence, the new land will begin to be expanded and its territory developed. With the rise of the economy and society, a management system will be needed, and from here, it could either become an autonomous region or continue to operate under the authority of the motherland. No matter what happens, this is the stage of maturity for the community, and we can look forward to its remarkable development in the future. By this time, the autonomous region will be complete, capable of utilizing the new land to create surplus value. At this point, the region can export goods back to the motherland, creating trade exchanges and boosting its own economy. The exportable products could be anything that the autonomous region can produce, or even things that are mined here. It could be oil, rare minerals, or even resources that the motherland doesn't have. By this time, the colonization of this island would be considered complete. The island now has residents, and life here will naturally evolve and improve. But up until now, we have only talked about colonization on Earth. So, what's different about colonizing Mars? As mentioned above, the first step is to find a target to colonize and explore whether it has the necessary conditions to support life and if the process of terraforming has potential. Fortunately for us, this process has already been completed. According to a discovery by NASA announced on September 28, 2015, we now have evidence that there is flowing water on the surface of Mars. Additionally, they found more than 5 million cubic kilometers of ice at Mars' northern pole, enough to submerge the entire surface of Mars under an ocean 35 meters deep. So, the biggest problem has been solved. We just need to find an effective way to get to Mars, and step 1 is complete. Fortunately, Elon Musk has already done this. So, step 1 has succeeded, and now we move on to step 2. The Martian atmosphere is almost non-existent, so the surface of Mars doesn't have oxygen to breathe, and the sun's radiation is deadly to anyone who stays outside for too long. The way to survive on Mars is by living inside sealed domes, isolated from the outside environment, and pumping in synthetic oxygen. As explained in the colonization steps, this is the phase where we will mainly rely on supplies brought from Earth. But we cannot depend on this for long, because the journey from Earth to Mars is perilous, and one mistake could lead to the death of the entire crew on Mars due to starvation. Therefore, astronauts will have to quickly create their own food supply. To achieve this, we can take inspiration from the movie The Martian by Ridley Scott. In this film, the main character creates a small garden to grow potatoes in order to survive. A closed greenhouse like this could easily be created on Mars, as long as we terraform the soil and provide the necessary nutrients for the plants. Over time, this will become the primary food source for the astronaut crew, and they will gradually become self-sufficient. Step 3. Self-sufficiency. To truly become self-sufficient, we need more than just potatoes in the garden. We need patience and a lot of time. During this process, we will gradually improve the Martian surface to make farming easier. In addition, regenerating the atmosphere will be an essential step for long-term survival here. This will be a very long journey, but it is not impossible. After terraforming the soil and atmosphere on Mars, we will gradually become independent and no longer rely on supplies from Earth. Livestock can also be brought to Mars to breed and provide long-term food sources for humans. With the vast amounts of water available, if we can warm Mars the way humans are doing with Earth, the seas will not be far on this red planet. At this point, Mars will have become a second Earth, with seas, trees, and a stable atmosphere to support development. We welcomed the first Martian children, and together we developed the population and began mining on this planet. As Earth's natural resources began to dwindle, Mars became humanity's promised land. Mars started exporting minerals to Earth, especially those difficult to produce or extract here, like nitrogen, ammonia, and unique minerals found only on Mars, along with compounds that could only be created here. As the economy grew, so did social stratification, and soon Mars had its own nations, each with its own government. This marked a huge step for humanity as we placed one foot on the next rung of civilization. Terraforming Mars was the first step toward achieving a Type II civilization on the Kardashev scale. We've actually made a video explaining the different types of civilizations based on the Kardashev scale. You can click the link in the comments to learn more. Specifically, this is a huge leap for humanity, laying the groundwork for expanding to other planets and becoming the dominant species in the galaxy. From Mars, we'll move on to more complex and hostile planets in the solar system, like Venus, for instance, and at some point, harnessing the full energy of the sun will become possible, and that's when we'll reach the peak of a Type II civilization. But, of course, all of this is still theoretical, still on paper and in the algorithms. We haven't faced the real challenges yet. There are many issues we still have to deal with, like solar flares, Martian dust storms, maintaining a stable economy during dormant periods, surviving on Mars for hundreds of years to improve the atmosphere, and many unknown dangers that may exist there. Despite these enormous challenges, humanity, once lost in the myths of gods in the sky, now ventures into space, exploring other planets. In just 100 years, humans have figured out how to turn a supercomputer into a phone, optimized rocket energy use, and accomplished many other miraculous feats. So, the dream of reaching Mars in this century is not impossible. Everything we will experience has already happened. The future is simply another form of the past. The first time you see Mercury, you might not think of it as a metal because it behaves like liquid. The first time you handle sodium, you might not believe it's a metal because it's so soft. In our subconscious, we always link new experiences with memories to make sense of what's happening. So, the past shapes the future, and the future is a reflection of the past. And that's what's happening with this universe. Humanity's curiosity and insatiable desire to explore have driven us to travel across the globe, challenge ourselves, and seemingly break through any limits. When we looked up and saw birds flying, we dreamed that one day we too could fly. And over time, we did. That moment of achieving the impossible made us look up at the stars, and we dreamt of landing there, just like the birds. And through time, we continued to learn, and that dream stayed alive until we realized what we were seeing were just illusions. Looking is a passive action. When you open your eyes, light hits the retina and sends signals to the brain to form an image. The limits of human vision are defined by the rods and cones in our eyes. We can only see a certain range of light. If the light falls outside the visible spectrum or doesn't reach our eyes, we can't see it. And that's what's happening in this universe. When we look up at the sky, we see stars and galaxies. Through telescopes, we see even more: nebulae, quasars, pulsars, and countless other wonders. But what we see isn't what we think. From the moment we were born, everything we saw seemed real and present. So we believe that the stars above us are right there, in front of us, and that, with a powerful enough spaceship, we could set foot on them. But reality is different. What we see is no longer there. Thunderstorms are a common occurrence that helps explain this phenomenon. When we see lightning strike, the thunder follows a moment later. This doesn't mean lightning and thunder aren't connected. When lightning strikes, it heats the air, and this sudden temperature change creates a shockwave. This shockwave reaches our ears, and our brain interprets it as thunder. The reason thunder comes after lightning is because it takes time for the sound to travel from the strike to our ears. The further the distance, the longer the delay between the two. This same theory can be applied to light, as light, like sound, is a form of wave. Light emitted from a source travels through space to reach our eyes. But because light moves at such a high speed, we perceive it almost instantaneously. However, in the vastness of the universe, light is not as instantaneous as it seems. Light traveling from one galaxy to another creates a similar delay to thunder and lightning. While light is on its journey, the galaxy it came from has already moved from its original position. So when we see that light, the galaxy is no longer where it was. Everything we see in the sky is actually an illusion. The things we see aren't where we think they are. In reality, due to gravity, by the time we see a planet, it's already in a different location. But in some cases, the things we see don't just move away, they completely disappear. And no matter how hard we try to find them again, we'll never be able to touch them. When you dip your hand into still water, the energy from the touch creates ripples across the surface. Light behaves the same way. It's the result of a specific energy source interacting with the surrounding space, essentially electromagnetic radiation. Just like waves on water, light also has properties like wavelength, frequency, and energy. The visible light we can see has wavelengths between 380 nanometers and 760 nanometers, a frequency between 430 terahertz and 790 terahertz, and energy from 1.7 to 2.0 eV, 3.3 electron volts. The most important property here is wavelength. Wavelength is the shortest distance between two wave peaks. The shorter the wavelength, the more powerful the wave. On the other hand, the longer the wavelength, the weaker the wave. Think of it like the beach. The further apart the waves, the calmer it feels. But when the waves come crashing in rapidly, you might feel overwhelmed. Light displays color through its wavelength. The shorter the wavelength, the more violet the color, and the longer the wavelength, the more red it becomes. From this, we can recognize that when light shifts to red, its energy has decreased significantly. This phenomenon is called red shift. Since light behaves like sound, you can experience this redshift effect when standing by the road. As a car approaches, the sound of the engine grows louder, but once it passes you, the sound fades and becomes quieter. This is the Doppler effect. This same thing happens with wavelengths as the energy source moves further away from the observer. Using the redshift mechanism and observing the colors of distant light sources in the universe, scientists discovered a terrifying truth. Over time, sources that used to be orange are now shifting to red, and the further away a light source is, the faster the redshift occurs. This means that cosmic objects are moving away from us, and the farther they are, the faster they're speeding away. Everything out there is slowly disappearing, and at an increasingly terrifying pace. And they're being left behind. Does nothing have energy? That's a complex question. But if we bring Einstein's theory of relativity into the picture, we might ask another question. If all matter has a certain amount of energy, does nothing have energy? When we look at the vast emptiness between the stars, we tend to think of nothingness as having no energy. However, when we sum up all the visible matter in the universe, we realize there's a huge gap in our calculations. Everything we can see, including stars, galaxies, and nebulae, adds up to less than 5% of the total matter in the universe. The sky is vast. Galaxies are even bigger. but they're just tiny specks in the grand scheme of things. So, we're just a minority, and the majority is made up of unseen matter and energy, which we call dark matter and dark energy. But the scariest part is yet to come. In 1998, scientists used the redshift of distant light sources and combined it with the total amount of dark matter and energy, and they discovered a terrifying truth. The dark space between the stars contains energy, and this energy is so immense that it's pushing visible matter farther and faster apart. If black holes are like massive gravity wells pulling everything in faster, dark energy has the opposite effect. It pushes everything away, and the speed is increasing. So most of the universe's energy and matter is in the dark void of everything. No one knows why it's there, and even Lawrence Krauss, the scientist who discovered this, can't explain it. But what we do know is that this energy is pushing everything farther and faster away. But how fast is it? Scientists have calculated the rate of the universe's expansion using various methods and have come up with a few numbers. For every megaparsec, the universe speeds up by 67 or 74 kilometers per second. The farther away something is, the faster it moves. With enough distance, some galaxies are actually moving away from us faster than the speed of light. Nothing can travel faster than the speed of light, or so we've always believed. But it turns out that nothing itself can. The infinite emptiness of the universe is stretching and pushing everything apart faster and faster. Even if we developed technology to travel at the speed of light, there would still be places in the universe we could never reach. So, what have we gained from this journey into the cosmos? We've learned that humanity has the potential to conquer almost anything. We can dream of becoming a civilization capable of reaching Type 2 or even Type 3 on the Kardashev scale, dominating the galaxy. With enough time, humanity can achieve incredible things. Yet, there is an invisible limit ahead of us, one that no one can surpass: the expansion of the universe. And that is the bittersweet conclusion of our journey through space. We hope that through this exploration, you've come to realize just how special we are, unique and also incredibly lucky as a species. But at the same time, we are so insignificant, barely even a speck of dust in the vast expanse of the universe.